Okay, thank you. And actually, there's quite a lot from that previous talk that we'll see some parallels with what I'm going to discuss. I'd like to start by acknowledging the person who did most of this work, Andrew Price, my former PhD student who graduated last year. And also we have some collaborators in Barcelona who have done quite a lot of work with these photoisomerizable surfactants and monolayers at the air-water interface. And what we've done, and I'll focus on in the talk today, is what happens when you make a surfactant monolayer at the nematic liquid crystal aqueous interface. In other words, a monolayer of a surfactant between an ordinary thermotropic nematic liquid crystal like a 5Cb and an aqueous phase. And if that monolayer is sensitive to light, what happens when you expose it to light? And the kind of the typical phenomenon that I'm going to report is shown here by polarized light microscopy, where if the system is in the dark and the photoisomerizable surfactant relaxes to its stable thermal form, you get homeotropic alignment of the nematic liquid crystal. But as you expose it to different wavelengths of light, we see different types of textures, different types that are due to changes in the anchoring of the nematic liquid crystal on that surfactant. And so this is kind of what I want to try to explain to you in 20 minutes today. So I can go pretty quickly, I think, through my introductory slides. Everyone in this audience should be familiar with the general idea of a liquid crystal and how its director is defined with respect to the azimuthal angle of anchoring and the zenithal anchoring. And of course, what makes liquid crystals interesting in this context is that they have this long-range order that can be probed by polarized light, but they're also fluid enough to respond to changes, and so we're very interested in looking at those dynamic changes. Here's the experimental system, and it's important to make sure you all understand this so you can follow the rest of the talk. So we have a liquid crystal phase. In this case, it's going to be a nematic liquid crystal. It seems like my pointer is going dead. Let's try this one. This is too complicated for me. I can't figure out where the button is. Ah, there it is. So the liquid crystal phase, nematic, and then we have an aqueous phase, and this is viewed between cross polarizers. And in the case where we have no surfactant adsorbed at this interface, the liquid crystal is anchored, has a planar anchoring at the water surface, and this bottom glass surface is treated so that the liquid crystal has homeotropic anchoring. So we have this kind of a mixed alignment cell, but it's birefringent, and we see all these birefringence interference colors in this sample. On the other hand, if a surfactant is absorbed at this interface, and if that surfactant is absorbed in a concentrated enough monolayer, then the anchoring at both interfaces is homeotropic, so we have a uniform homeotropic cell, and it's dark between cross polarizers. And what I'm going to show you is that based on subtle changes in the structure of this monolayer, you can get different kinds of anchoring besides just planar and homeotropic, and that's the basic phenomenon. Okay. So we've looked at this system, and other groups have as well, using different types of surfactants. The favorite kind of model system when people are interested in looking at surfactant monolayers is long-chain saturated carboxylic acids, fatty acids, because those monolayers of like stearic acid and such have been studied for a long time at the air-water interface, and for about 10 years now, I think this phase diagram of fatty acid monolayers at the air-water interface, so-called Langmuir monolayers, has been determined, and it's a pretty interesting and complicated and maybe a little bit frightening phase diagram, because there are a tremendous number of phases as a function of surface pressure on the vertical axis and temperature on the horizontal axis, and these are all names given to different types of arrangements of the molecules within a molecular monolayer. Many of these phases are hexatic mesophases that are either tilted or untilted, and they may be tilted towards the nearest neighbor or between nearest neighbors. But in any case, these phases have all been characterized using grazing incidence X-ray diffraction and microscopy techniques, and there's a lovely review article out there if people are interested. But we found that one could also absorb monolayers of these same fatty acids at the nematic water interface, and depending on the concentration of the fatty acid at the interfacial layer and the way the molecules are organized, we got different types of anchoring. So, for example, if the fatty acid molecules, these surfactants, were very dilute at the interface, then it was essentially as if they weren't there, and the liquid crystal molecules adopted a planar anchoring. If the molecules were more concentrated at the interface, but in a disordered way, then one observed homeotropic anchoring at that interface. But in some very densely packed phases where there was liquid crystalline order in 2 dimensions within the monolayer, if those molecules had a coherent tilt angle, then that tilt angle was also transmitted to liquid crystal, and so we had an intermediate type of anchoring, and we saw birefringence. So here are some pictures of what I just showed you, some actual pictures showing birefringence. If in this, what we call the 2-dimensional gas phase, when the monolayer is very dilute, we see these types of birefringence colors, which correspond to planar anchoring of the nematic crystal. And here is a 2-dimensional liquid phase of the surfactant, which leads to homeotropic anchoring, but at even higher concentrations of the surfactant monolayer, we see phases that have these, where you see these colors, these birefringence colors that indicate just kind of a small tilt away from homeotropic anchoring, but these large lateral domains where that have different colors, which indicate different azimuthal directions of tilt. And so these are kind of characteristic textures of 2 different tilted hexatic mesophases at the interface, and how they change the anchoring of the liquid crystal. And these, this is just a one component monolayer, and in order to go from one phase to another, one has to change the concentration, or one has to change the temperature. What I'd like to talk about today is if instead of using an ordinary saturated fatty acid surfactant, if we use a fatty acid surfactant that has this azobenzene group incorporated into the chain, which allows us to switch between this trans and this cis conformation deliberately by illuminating the sample with different wavelengths of light. And I want to show you a video of what happens if we expose an optical cell where originally all the surfactants at the interface are in this trans state, and then we expose it to visible light, which is going to convert some of the molecules as a function of time into this cis state. So we have originally all homeotropic anchoring, and we see colors that are corresponding to a small tilt angle away from homeotropic, and of course a lot of defects. So we now have tilted anchoring throughout the cell. Now we start to see some homeotropic regions reappearing. Finally breaks up into what I'd characterize as lateral coexistence between some regions with homeotropic anchoring and some regions with tilted anchoring. And that's where it ends. That becomes kind of the new stable state when illuminated with this particular wavelength of light. So it's pretty complicated. This effect, by the way, is reversible. If we allow it to thermally relax, it will go back to this through the same sequence of phases. Let's look a little bit more closely with some. I've now selected some images out of the video where we started by allowing the optical cell to come to equilibrium or to a stationary state, illuminated by 436 nanometer light, and we saw this type of phase coexistence is hard to see because the domains are very small. And then we instantaneously changed the wavelength of illumination to this near UV, 365, and that's known to convert a lot of the trans isomers to cis isomers. And we go through this sequence of phases. First, we see uniform tilted anchoring, and then we see some homeotropic regions appear that it becomes all homeotropic, and then we see this other phase come in with very large tilt angles. So if we turn off the 365 nanometer light and go back to 436, this sequence reverses, and so this has all the characteristics of various kinds of phase transitions going on: phase coexistence, reversibility. And so our hypothesis is that what's going on is that as we change the wavelength of illumination, we're changing the composition of the mixture in the monolayer. We're starting with a certain mole fraction of trans to cis ratio, and we're changing that ratio. And as we change that composition, we're moving across a phase diagram and in 2 dimensions, and those 2-dimensional phases are being protected by the anchoring of the liquid crystal phase. Just to show you how that happens, this is a standard kind of an azobenzene absorption spectrum. This is the absorption band of the trans isomer. So if we illuminate in here in this 300 to 400 range, we'll trigger a lot of the trans to cis isomerizations. But if we illuminate at say 450, we convert cis back to trans, and of course thermally, slowly cis relaxes back to trans anyway. But what's interesting is that if one chooses some kind of an intermediate wavelength to illuminate these fluorophores at, you'll have some flux, some absorption of trans being converted to cis, but also you have some cis being converted to trans. So depending on exactly what wavelength you choose to illuminate at, where these 2 bands overlap, you end up with a distinctive mixture of the 2. That's called a photostationary state. And so by tuning the wavelength of the light which we illuminate in this region where these bands overlap, it's kind of a surrogate for changing the mole fraction of cis and trans in a systematic way. So if we look now not at dynamic changes that happen when we instantaneously change the wavelength, if we look at photostationary states at different wavelengths, we see very similar sequence of phases. In the dark, in the all-trans form, we see homeotropic anchoring. At 436 nanometer illumination, it comes to a stationary state that indicates phase coexistence within the monolayer, where there's one phase gives tilted anchoring and the other gives homeotropic. As we continue to get more cis in the mixture by using lower wavelength, we see uniform tilt, and then at even higher cis fraction, we see a homeotropic phase in equilibrium with a phase that gives very high tilt. What's interesting here is that the way the system looks when illuminated with 405 nanometer light depends what the previous wavelength was. If the previous wavelength was higher, then we see uniform tilt. If the previous wavelength was lower, then we see phase coexistence. And this is the kind of hysteresis that you typically see in a first order phase transition. And so it is reversible, but with hysteresis. So we're kind of following the standard approach when one sees a phase diagram, which is give names to phases and then map it out. Maybe I should just stand still. And so at a constant temperature, we're able to kind of identify several phases that we call T1. T stands for trans, and then we see this mixed sub T, M sub T phase, and then M sub C phase, which also gives homeotropic anchoring. But it's not the same phase as this T1 phase. It's disconnected on the phase diagram. And then as you go more to the cis side, you see this very birefringent phase. Presumably, if we could get a completely cis monolayer, it would be uniform in this, this tilted phase. And then at low concentrations, we see a vapor phase with the expected kinds of phase coexistence in between. So we can be a little bit more quantitative by using different concentrations, different wavelengths of illumination. That is basically how we change the composition of the monolayer. And so this is like a surface concentration, if you will, like a surface concentration or surface pressure composition phase diagram at a constant temperature, where we've just given these phases names based on their composition because we don't know what the structure of the phases are. And we've taken a little bit of artistic license with the really specific shapes of these boundaries because we've measured the phase behavior at various points on the grid, and so we know that the topography of this phase diagram is correct if we don't know exactly the shape of all these boundaries. We do see, for example, that at lower concentrations, the transition between these two mixture phases goes through phase coexistence, so it's first order, but then at higher concentrations, it's a continuous transition. So there's a lot of, kind of interesting things that we see in these monolayers, the same kind of richness that one sees in monolayers at the air-water interface. We've also looked, that was a typical phase diagram at close to room temperature. And when one changes the temperature over a range of like 5 degrees C to 40 degrees C, the same phases are seen where the phase diagram shifts a little bit, with the exception of one phase, which is this T1 phase, the trans. At low enough temperatures, we see a phase that has uniform tilted domains. So we've mapped out phase diagrams at all these different temperatures, and there's a lot of detail here, but that's kind of the point. And I will just mention that our collaborators have done quite a lot of work, and that's been published, looking at monolayers of these fatty acids at the air-water interface using Brewster angle microscopy. And while they see a phase that corresponds to the all-trans monolayer, which is tilted symmetric C type phase, and a phase that's completely isotropic for the cis, and they see phase coexistence. That's all they see. They don't see the same kind of richness that one gets in the phase diagram at the nematic interface. So it seems that the interaction of the nematic phase with this monolayer is causing a much more complex phase diagram to occur. So what we think we're seeing is that illumination in different wavelengths creates different photostationary states with different isomeric ratios. And at the nematic aqueous interface, we see a very rich phase diagram with 5 or 6 different phases that appear at different temperatures and compositions. And that these different two-dimensional phases result in different types of liquid crystal anchoring. We see homotropic anchoring, planar anchoring, a small tilt angle anchoring, and a large tilt angle anchoring. And that by choosing the surface concentration and composition, and one can of course choose that composition by changing the illumination wavelength, one can direct what type of anchoring one gets dynamically or including mixtures, coexisting regions of those different kinds of anchoring. So I'll leave it there, and thanks for your attention.
Yeah, let's say. Okay, so we have time for just one quick question, please.
When you use photoisomerization, does the concentration of this process in acids remain the same?
Did everyone hear the question? When there's photoisomerization, does the concentration remain the same? So I assume you mean the concentration at the interface. We don't really have a way to directly know that because the monolayer is in equilibrium with the small concentration that's actually dissolved in the liquid crystal phase, which is how we introduce it. But based on the types of phases that we see, we don't think that the surface concentration changes much. In other words, that all the phases at a given bulk concentration are consistent with the types of anchoring that you see for approximately the same concentration. But I would suspect that the solubility, for example, of cis formed in the liquid crystal and the transformed liquid crystal might be a little bit different. But it's coming to equilibrium at each case, in each situation.
Okay, thank you very much. So before we will go for our lunch, there will be a final highlight presentation by Daniel Cox from University of California, Davis. He is also the co-director of the International Institute of Complex and Adaptive Matter. So the lunch will be provided